In this video, we start section 3.9, which is logarithmic differentiation. First, we do a review of logarithm properties and the derivatives, and then we do logarithmic differentiation. So the discussion is, what is the first thing to cover is that what is the definition of a logarithm? If you remember, if y is log base b of x, then that means that b to power, that means b to power y is going to give you x. And so it's b to power y gives you x. So now we're thinking, okay, so that's the first thing. And then, so what are the properties? Some of the properties of logarithm is, and the first thing is exactly restating in a definition. So if I say b to power y, y would be the log base b of x, and I'm saying b to power y is equal to x, so b to power log base b of x is x. The other one also comes from similar sentiment. If so we're saying that log base b of b to power x is equal to a y, and then that y has to be equal to b to the power x. That means y has to be equal to x. And then all of these following, and we've seen in pre-calculus, and we've seen why they work. These two come from properties of exponentials. If you rewrite these, the log with use of the definition of the logarithm, then use the exponential properties, then you come with the property 2 and 3. The three properties that we see come in handy a lot, not only in Calc 1, but in the Calc 2, Calc 3, and when you get to mathematics that is not calculus anymore, differential equation, and so far and so forth. What happens is that a lot of times when you take derivatives, using these properties make the derivatives simpler and easier to manipulate. And so you want to learn those very well. And then the last but not least is this property that basically log base b of x to a power is going to be that power times the log base b of the base of the inside. So how do we, and I sometimes try to memorize this by making them into words. Somehow this one is log of a product is equal to a sum of logs, and then this one is log of the quotient is equal to the difference of two logs, and then log of an exponential is exponent times log of that base. And so that makes it a little easier to memorize and remember. Another review here is the derivative of logs. And when we have log of log base b of x, and we take the derivative of that, then it would be 1 over x times natural log of b. That makes the derivative of the natural log of x to be 1 over x, because log ln of e is going to be equal to 1. So let's try to remember some of these properties. And so the first one is, what does log base 4 of 16 equal to? If you remember, log base 4, and 16 is actually 4 to power 2. And if we use that property of the log of exponential, then 2 comes down and goes log base 4 of 4. And then one more process is logarithm of base b of b is going to be equal to 1. So the entire thing becomes 2. Then if we're discussing log base 4 of 1 over 16, how does that work? Can I write the inside as a number that is that x base 4 to a power? And so yes, I can, and that would be 4 to power 2 is 16, but it's 1 over 16, so it's going to be -2. So the entire answer is going to be -2 times natural log of 4, and that is equal to -2. Now let's do a few more of these. What about log of base 1/4 of 1 over 16? 1 over 16 is 1/4 to power 2, base 1/4, so 2 comes down, and there will be log base 1/4 of 1/4, and that's equal to just 2. How about this one? And if I'm taking the third root, that means it's 2 to power 1/3. And therefore, 1/3 comes down, and it becomes log base 2 of 2 times 1/3, and which is 1/3. How about this one? So here base is 2, and then it's 1 over 4 times square root of 2, which means it's the bottom is 2 to power 4 is 2 to power 2, and square root of 2 is 2 to power 1/2. 2 and 1/2 add up to be 5/2, but since it's the denominator, it's going to be in the denominator, it should be -5/2. So you're really finding log base 2 of 2 to power -5/2. The bases are the same, and you get -5/2. How do we simplify this one or expand this one in a way that makes it easier to manipulate? And when I say manipulate, I like to talk about taking the derivative. In this case, if I expand this, it's going to make it a little easier. So it's natural log of a quotient. So I can write it as the difference of two logs. The numerator, then minus the denominator. And then the numerator was a product, so I can log of product is going to be the sum of two logs. And then after that, we're going to have this, the square root of x plus 1 is actually x plus 1 to power 1/2. So it's going to be 1/2 of natural log of x plus 1. And that would be the final answer. So now let's do an iClicker. Find derivative of f if f of x is equal to natural log of pi. How do we find this? So please pause your video and think about it. So let's come back to this. We're saying f of x, f function of x, is equal to natural log of pi. If I plug in pi in natural log, I get a number. It's going to be an irrational number, but still is a number. It's a constant. So when I take the derivative, it has to be that one. Another iClicker question. Find the derivative of f of x if f of x is equal to natural log of x squared plus 1. So I'll give you a minute to pause and think. I hope you paused and think. And you paused and gave it a little bit of thought. And so now let's try to solve this. And so from what we know, the outside function in here is the natural log of x, or natural log of u, as we can say. So I have to think about what is the derivative of natural log of u. And that would be 1 over u. And so the derivative here is going to be, that's the derivative of outside. When I plug in the inside, then I take the derivative of inside. So what's the derivative of u? That would be 2x. And which one is the answer in here? That one is the answer. So if you remember from the pre-calculus, natural log base b of x is the inverse function to y equal to b to power x. And here we're assuming the picture that we give is the b bigger than 0. Otherwise, it would go the opposite direction. In either case, b bigger than 1. If b bigger than 1 or b is smaller than 1, bigger than 0, in both cases you will have that output of the exponential function is going to be always positive. And therefore, the domain of logarithmic function is always going to be the positive numbers. And so a lot of times, though, we want to have more values to put in input. So a lot of times you see that people try to do something, so they include more values for the logarithmic function. Here's the logarithmic function. Oh, I crossed the y-axis, which I shouldn't have, because it doesn't go through that. So when to actually take care of the domain issue, instead of calculating natural log of x, we calculate natural log of absolute value of x. And in this way, the input is going to be all the negative numbers, all the positive numbers, not the 0. So what does it, and the next thing is that, what does it mean, ln of natural and ln of absolute value of x? That means, as you remember, we have to figure out where inside the absolute value is positive and where the inside the absolute value is negative. In this case, I'm not even including 0. And so when inside absolute value is positive, this is just ln of x. When inside absolute value is negative, this is ln of, or natural log of, negative x. And then you want to take the derivative of that. And how does that work? And then that would work. So before that, I want to show you how does the graph look like. The graph of natural log of absolute value of x is defined both ways. See, this branch is this part, and that branch is natural log of negative x. That only takes the negative parts of the number line, basically. And then from there, we want to find the derivative of this function. Let's look at this. If I'm taking the derivative, then derivative is going to be, for x bigger than 0, derivative of ln of x is just 1 over x. For x less than 0, derivative of ln of negative x is 1 over negative x times the derivative of inside, right? That's the outside is 1 over u, and then derivative of u, which is going to be -1. Oh, these two negative signs simplify, so even for this part you get 1 over x, and that's what you get down here. And so this becomes the formula. Derivative of natural log of absolute value of x is 1 over x for all x that are not equal to 0. Not only derivative of natural log of x is that, but not derivative of natural log of absolute value of x are the same thing. Let's try to do this iClicker question. iClicker question 3 of section 3.9. Find the derivative of f of x equal to natural log of absolute value of x squared minus 1, and then find the domain of f prime of x. I'll give you stop the recording and think about it. So now I assume that you stopped the recording, so let's start solving it. So we have natural log of absolute value of x squared minus 1. I can either go with the formula that we just drove, or I can start my new formula. And let's see. If I'm talking about natural log of x squared minus 1, absolute value of x squared minus 1, that is a natural log of x squared minus 1 if x squared minus 1 is bigger than 0, or it's natural log of negative x squared plus 1 if x squared minus 1 is less than 0. So that's again a piecewise defined function, and when I'm trying to take the derivative of that, let's put the derivative on all of them. d dx, d dx, and d dx. This one gives me 1 over x squared minus 1 times 2x. That one gives me 1 over x squared minus x squared plus 1 times negative 2x. And the negative signs simplify together. Both of them become 2x over x squared minus 1. 2x over x squared minus 1. So derivative I figured out. 2x over x squared minus 1. I have at least 3 of the options are that. So what would the domain be in this case? Let's think about it. 2x over x squared minus 1. What makes this not exist when the denominator is 0? Denominator is 0 at 1 and negative 1. So we have to exclude 1 and negative 1. And so what are the options in here? So we see the options. We had 2 options that actually the derivative was correct. Now out of the 2 options, one of them has the right things taken out. You don't need to take 0 out over there. And so that's the answer.